I'm recording. So.
Welcome everyone to our transportation seminar series, seminar series at ICT. And again, I'm happy to be here once in a while, right? Introducing the speaker. For today, we have actually Priyanka Sarker is going to be making the presentation, and it's on a topic that we are working together in an ICT project. And a little bit about Priyanka. Priyanka started with me, I think, 2 years ago, in about 2012, and she came to U05 from University of Akron. That's where she did her master's work on some pavement marking study. And then I think she's originally from Bangladesh. But for 2 years, we've been running the FWD polymer deflectometer device. Basically, we had to reassemble it with the help of research engineers here and going out to local roads and streets and doing basically FWD testing to assess the structural condition. And all for the effort of basically coming up in this project with overlay thickness designs for low volume roads based on non-destructive testing and evaluation of existing pavements. So she's going to talk about the project progress and other things that are going on in the project as findings. We're coming close to actually finishing the project now. So with that, I'll
Thank you.
Priyanka take the stage. Yep.
Okay, good afternoon, everyone. As the professor mentioned, this is basically based on FWD testing, and we are trying to develop a new method, a mechanistic-empirical approach to develop overlay thickness design procedures for low volume roads in Illinois. And here's the outline that I'm going to follow in my presentation. First, I'm going to talk a bit about the background, introduce you to the problem itself. Then I'll mention the research needs, why this research was important and why we initiated it. And then I'll give you a brief overview of the current overlay design methods that are being used. Then I have selected a couple of case studies to show the results to you. And then I'll talk about the proposed mechanistic empirical pavement design approach to do an overlay design. And in the end, I'll take questions. So first, the background. As most of us know, one of the most common maintenance and rehabilitation strategies is for flexible pavement. It's basically a placement or installation of an HMA layer over the existing pavement structure. And in Illinois, what the agencies do is that they design this overlay thickness requirements for low volume roads based on an old empirical AASHTO design approach using some modified layer coefficient values. And this layer coefficient values approach is basically very simple, very straightforward, but it's simply outdated because we only have a bunch of those values available for a limited number of materials. So these values are not sufficient enough to characterize the recent materials which are being used in pavement construction, and they're not suitable for considering the effects of recycled or other non-traditional construction materials. So, and also, since they don't do any kind of structural assessment testing, no mechanical testing is done or whatsoever for evaluating the structural condition of existing pavements, this often leads to an uneconomical practices as far as the rehabilitation of the low volume road is concerned. Because what happens sometimes is, if the pavement is, let's say, it's actually in very good condition, but probably the design will say or it will come up with a very thicker design requirement, which was actually not needed. So you will have a expensive cost of construction. And sometimes it can also happen that the pavement was actually in very bad shape, but the design requirement said that you only need a thinner overlay requirement. So in no time the pavement will fail and you will need another overlay. So sometimes this can often result in uneconomical practices. So it's very important to do a proper structural condition assessment of an existing pavement structure before any kind of overlay design is done. So, and it can be properly accomplished by the use of a non-destructive testing equipment such as the falling weight deflectometer. So what a falling weight deflectometer does is basically drops a load, a weight on the pavement surface, and there are a couple of sensors, those deflection sensors, that are installed at various offsets from the center of the loading plate, and these deflection sensors, they basically measure the deflection of the pavement once the load is dropped on the pavement surface. And from those deflection measurements, the layer properties, as in the layer moduli values, can be determined through a back calculation problem, which is basically an inverse problem. So in addition to determining the moduli values, just by looking at the center deflection from the FWD deflection bowl, one can tell how the pavement is overall doing structural condition-wise. If, like in this figure shows, if the deflection is a lot, so it definitely tells you that the pavement structure is basically weak. Well, while if the deflection was comparatively low, it will show that the pavement was very, like, in a good health. It was a strong pavement structure. And also, apart from looking at the center deflection only, the whole FWD deflection bowl also tells a lot about the overall structural condition of the pavement, such as it has been shown that the FWD sensors that is installed at 1.5 HP, which is basically the total pavement thickness over the subgrade, this deflection measurement measured at that sensor basically picks up the deflection that is coming from only from the subgrade, and it's not being influenced at all by the surface layer or the base layer. So if somebody takes a look at that measurement, one can tell that how the subgrade is doing under the traffic load conditions. There are other indices as well, like base curvature index, surface curvature index, to characterize the deflection basing. So what are the benefits of using an NDT-based overlay design method? First of all, since we are doing a proper structural evaluation using an FWD, so we are relying less on the human judgment. Because if we were just assigning a random structural number, layer coefficients to each of the layers, it involves a lot of human judgment. And so using of an NDT-based design method would definitely lower the reliance on the human judgment. Then we are directly estimating the existing pavement layer moduli from the field without doing any kind of laboratory testing. And also it's less expensive, as the expenses and inaccuracies associated with destructive testing of the pavement components are no longer required. And since we are designing an overlay thickness based on a proper structural condition assessment, it means that whatever we are designing, whatever we are coming up with, it is expected to match better the pavement service life. So what are the research needs? I mean, in Illinois, many local agencies are resistant to using FWD testing, despite of having a number of advantages. First of all, that it requires a high initial cost because you have to pay someone to go out there to do the testing and the subsequent back calculation processing. So many local agencies don't want to bear that cost, and also there is a lack of understanding of the whole process and the evaluation thing, how it goes. So what they're doing is basically they're using a modified structural coefficient procedure. It's basically it has been adapted from the 1960 AASHTO road test, and like I've said before, it's very simple and straightforward, but it's very, very totally outdated. So addressing those research needs, the objectives of this research was to develop an HMA overlay thickness procedure for a number of local road and street projects using this FWD testing and pavement layer moduli back calculation, and to demonstrate the advantages or disadvantages associated with the approach with each design alternative, and also to show that through non-destructive testing, improved HMA overlay thickness design procedures can be developed that would be reliable and cost-effective overlays for local roads. So the first task was to evaluate the existing overlay design procedures and conduct a sensitivity analysis to determine the effect of each input design parameter on the final overlay thickness in any specific design method. And what the sensitivity analysis does is that it basically studies the behavior of a complex model to determine the variation of each input parameter's influence on the response of the model. It primarily observes how sensitive a system is to the variation of the system parameters around their typical values. In order to do so, we took a look at the existing overlay design methods, and we found out that there are two methods. One is based on the concept of structural deficiency, which is being followed by AASHTO 1993 NDT method, and also the IDOT procedure. And another one is based on the concept of maximum deflection and effective thickness, which is being followed by Asphalt Institute method. So here is a flowchart that shows how the AASHTO 1993 NDT method works. I'm sure a lot of you already know about it. Just to refresh your memory, we need the deflection data, just the center deflection, and we'll normalize that to a 90 drop load, and we'll conduct temperature adjustment. Then we'll calculate the subgrade resilient modulus using this equation, and estimate the effective modulus of all pavement layers above the subgrade using some other equations. So what it does is basically it assigns one structural number based on the layers above the subgrade, and then from the effective structural number, we can estimate the overlay thickness. So this procedure basically estimates the structural impact of the overlay in terms of effective structural number by adding the value of the overlay in a way that it was assuming that it was part of the original structure. But if we follow this procedure, one should keep in mind that effective structural number doesn't always necessarily portray the existing structural layer moduli value, because one structure with a low structural number can also have a higher layer moduli. On the other hand, a higher structural number can also have a lower structural layer moduli values. Here's what the IDOT does to design an overlay thickness. All it needs is the pavement cross sections, and then it assigns it has this table that has a number of layer coefficient values, and so based on that values and the thicknesses, it calculates this effective structural number. Then from the traffic factor, which is basically calculated from easel, and IVV value, we have normal brush to calculate the required structural number, and then it estimates the overlay thickness from the required and the effective structural number. This is what the Asphalt Institution deflection-based method does. Basically, what it needs is Bankfeldman deflection measurements, and then it needs projected overlay traffic, temperature adjustment factor, and critical adjustment factor. Then it has a bunch of normal graphs and equations and everything to solve for the overlay thickness requirements. So after we did all the sensitivity analysis, I'm just showing you the results. We came to see that in modified AASHTO procedure, the HMA and base layer coefficients were more sensitive to the output of the overlay thickness requirement. And in 1993 AASHTO method, it was shown that the surface deflection varied the most with the overlay thickness requirement, and the representative rebound reflection was the most sensitive parameter in Asphalt Institute overlay design methodology. So our next task was to establish local road and street demonstration projects where we'll go out and conduct availability testing and use those test data to come up with a mechanistic empirical approach. So in order to do that, we sent out a survey to the local agencies around us, and based on their responses, we selected a number of local candidate projects, and the criteria that we kept in mind was that these roads were showing some kind of distresses and were in need of rehabilitation. And then we went out and we covered, at least I think we went to 6 counties in Illinois, and we covered more than 20 locations. But in this presentation, I'm going to only show you 5 sections which were located in 2 counties in Illinois. And as you can see in these pictures, here the section that we covered, and section 1 and 2, they're basically part of the same location, but they have different layer thicknesses. Same in the case for section 3 and 4, where 3 and 4 are basically going opposite direction, but they have different layer thicknesses. And section 5 is basically, that's only one section. The thicknesses didn't vary along the section, so we consider it as one. And the table shows the number of times we went out there to do ability testing. First, we went to do our set 1 testing when the pavement conditions were shown to be severely cracked and they definitely needed an overlay. So we went to all these 5 locations and we did our ability testing. After that, 4 of these locations, namely section 1 through 4, they received an overlay. So we went out there again and did our ability testing. 1 year after the set 1 testing effort, we went to do another set of ability testing just to see how the pavements were doing. So these are some pictures from our testing efforts. As you can see, the top picture at the left, it's the section 1 and 2. It shows how much cracked the pavement surface actually was, and it definitely needed an overlay. Same goes for the case of section 3 and 4. And the bottom pictures show how the pavement was looking after they received and thin overlay. And this is one year after we did our first set of testing, and it was seen that the pavement was still doing fine. There were no sign of cracks or whatsoever on the surface of the pavement. And this is section 5. Please note that section 5 never received any kind of overlay, so we just went out there twice first, and then we went out again 1 year after the initial testing effort. And it also showed to have, it also required an overlay, but somehow the agency haven't installed one yet. So this is basically the various cross sections of these 5 sections. And then we did our analysis. We wanted to see if we were following AASHTO 1993 and IDOT methods, how much will be the overlay requirement. And it was seen that according to 1993 AASHTO method, most of these sections were doing just fine and they didn't need any overlay. And for IDOT method, it was hard to calculate because we didn't know actually the original structural conditions of these pavements. So I just used the typical coefficient values from the table and tried to come up with an overlay requirement. And it did show that these pavements all need roughly from 10 to 21 millimeter of overlay. So our next task was to develop and improve overlay procedures based on our FW testing and AMI concepts. So what we did was we're trying to develop this AMI analyze-based approach, and here's the flowchart. So basically what we do is, after we obtain our FW deflection basin, we analyze this deflection data to back calculate the layer moduli values. Then we adjust the layer moduli by analyzing the deflection data, and we use ILIPAVE, ANN Pro and Visor. Then we iteratively adjust the overlay thickness to ensure that the critical responses are lower than the threshold values for the design easels. And here are the 2 damage models that we're using in this analysis. So what we mean by doing a layer adjustment is that we want to model the actual deflection basin through ILIPAVE, and and this table basically shows all the values that we came up with. And so what we did is we used ILIPAVE and we ran those analyses, and we extracted the deflection values at different offsets from the loading plate. And we wanted to make sure that the predicted deflection that we are predicting using ILIPAVE was actually higher than the average of what we had from the field. So this graph basically shows how we predicted the deflection using ILIPAVE. And then we wanted to see, after we modeled and everything, we wanted to see if there was any overlay requirement according to this approach. And we saw that we needed all these 5 sections actually needed an overlay based on these AMI responses. And if you remember, those sections didn't need anything according to IDOT and AASHTO procedure. So this AMI method actually captured the structural deficiency of the existing pavement accurately. And this table shows the what we had after the overlay was done and 1 year after the initial testing report, the table at the left. So if you remember the section 1 and through 4, they received, actually they were overlaid with 1.25 to 1.5 millimeter of HMA. So after we did our FW and everything, we saw that the pavement was actually doing fine. The overlay requirement satisfied the mate. And after 1 year of the initial testing effort, we went out and again we did FWD testing, and it was seen that the pavement was actually also doing good. And remember section 5, it never did receive any kind of overlay. So according to ME approach 2, it was seen that the capacity was actually greater than not greater than the demand for a design period of 20 years. So this table shows a comparison between the AASHTO 1993 IDOT and the proposed ME methods. One thing to notice from this table is that how we are characterizing each layer according to different methods. I mean, for AASHTO 1993 method, we just assign one structural number to the whole surface and base layer, to the whole structure above the pavement. And wherein our ME method, we assign a constant modulus for structure surface layer. Then we use K-theta model to describe the base layer, and we also assign another constant modulus to the subgrade layer. And also the ME method, the consideration of the non-traditional materials can be directly incorporated through K-theta model, wherein IDOT model is not capable of considering the effect of those recycled materials. And for AASHTO method, the effect can be indirectly considered somehow through FWD center deflection. So in summary, these results that I'm presenting here is part of this ongoing ICT research. And in short, we selected 5 different sections, and 3 sets of FWD tests were conducted over a period of 1 year. And we used the 2 commonly found overlay thickness design methods, and it was seen that all these pavement sections were characterized as structurally adequate by the 1993 AASHTO method. And in the end, we developed a mechanistic-empirical method to design overlay thickness for low volume flexible pavements in Illinois. So, and if this proposed method was found to adequately address the current structural conditions of the existing pavements. So all these results have been put together in a paper and has been accepted for presentation and publication for the next TRB meeting. And I want to acknowledge Scott Lackey, which is our TRP chair, and Kevin Berg, then Dr. Dev Mishra, James Foran, Chief Master, for all their help and valuable support to the project. Any questions?
All right, any questions? Would you back up to that one slide you were doing the comparison? There you go, okay. Surface layer, you're saying you're constant modulus, and then you're also using a constant modulus for subgrade?
Yeah, we couldn't do the bilinear subgrade model, so we just went ahead and put one values. So
why did you do that?
At this time, it's hard for us to, I mean, because we're just trying to model the FW deflection data through the ELIPAVE, and the back calculation software that are available right now, they also just come up with that constant modulus. So we are using actually those modulus as a base value. So that's why I didn't do any bilinear subgrade model.
Basically, it was the ERI input with the ELIPAVE.
Yes, yeah.
So
input with the ELIPAVE, but
that's
it was
the only input needed.
No,
but it takes into account the bilinear model.
No, we didn't consider the bilinear. We used just one. Yeah, because that's what your modulus, all those back calculation software gives you. That's why.
Excuse me, may I have a question? And then can you return back to the pictures of pavement cracking? Go back. Yes, I want to know, and how many years after use it will be so many cracking of the pavement to have the.
We don't really have the data. I mean, this pavement, I believe they told us it was constructed back in 1985. So, but they do a thin overlay from time to time, but they don't really have much of a history available for us.
And so, the pictures at the bottom is a new road.
Yeah, after the overlay was installed, right after the overlay was installed, and this is 1 year after the overlay was installed.
Yeah, another question is, and if you use your method, you named ME, and how to guide to build a new road, and to build a new pavement, and how to use your method to guide to build a new road.
This is an overlay thickness design approach. Overlay thickness, rehabilitated pavement, not a new one in this case, in this project.
Thank you.
What was the original thicknesses of the initial pavement section 1 and 2 and 3 and 4? How much asphalt was there?
They had 2.25.
Quarter?
Yeah.
When you back calculated the modulus of the asphalt,
Mm-hmm.
did you just assume the thickness of the overlay?
Uh,
or the total thickness of the overlay plus the original asphalt layer?
It depends on, like, if we're doing it before the overlay, then yeah, I only considered the existing one. We did evaluate 3 times. So 1 before the overlay and 2 after the overlay. So after the overlay, I considered both the existing thickness and the overlay thickness.
The after overlay picture is actually after that winter, this past winter, correct?
Yeah.
So overlay survived that winter.
Yes, it did.
Mazer asks a question online here, and he would like to know, how do you consider the asphalt mixture properties as well as viscoelastic properties depending on the temperature of the pavement on the final overlay design?
Well, at this point, we are just assigning the moduli values, so we are not considering the temperature variations or viscoelastic properties.
Well, we normalize deflections to
Yeah, for the AASHTO, yes.
68 degrees
68 Fahrenheit.
How do you normalize the temperature?
For the AASHTO one, I use their chart. They have this chart based on the center deflection.
Any other questions? Comments?
Oh,
All right.
So, Yoanji would like to know, how does the ME method proposed address the unavailability of model parameters of the nonlinear base subgrade resilient modulus models, as well as the seasonal moisture and temperature dependence of asphaltic and unbound pavement materials?
So we are doing the design based on what we have, based on what we have the deflection data as of now. So we're just using the elliptic to to model the deflection data, deflection basin found from the field. And that's how we're incorporating all the material properties. And at this moment, we're not doing any seasonal effect or seasonal adjustments.
So you wouldn't specify with the binder a different binder grade based on what temperatures it would see. You would just say what thickness it needs to be, assuming that the binder was correctly chosen.
I will just assume, I will just give a moduli value like, okay, we need at least this.
Yeah, but the moduli value would change.
Yes, I understand what you're saying, but just a range.
Okay.
One quick comment, actually, and hopefully you can hear us too. Well, this project is intending for local agencies to actually start to use what has been established for mainline highways for many, many years. Every state DOT has an FWD device. Every state is using FWD testing as structural condition assessment. However, when you look at local roads, which are really not getting so much attention paid,
they never actually end up doing this, local agencies. And this is a implementation practice project, which is how can we actually demonstrate that this would be, even though upfront may be a little costly, but down the road this will be a better thing to do than just using the modified layer coefficient approach. Because you're totally blind in that approach by assuming layer coefficients. You don't have any means of assessing the structural condition of the existing pavement. So basically this is an implementation project, and that's why such details, I guess, on the asphalt, and we're all at the university level here, and we're very interested in details, obviously, all deeper in every layer properties and things, but still, some of those things, probably not the discussion point at this time, but rather seeing what is commonly used as for non-destructive structural condition assessment in mainline highways to be applied in local roads, to get them to realize that this is available, and this may be even eventually less costly when you consider the life cycle costs and sustainable pavements and all that stuff. So that's the whole point of this project.
One more question. Zara wants to know, have you already done any life cycle analysis and cost evaluation to assess how much we are obtaining using this method?
Not any life cycle analysis has been done yet to this point, but we are looking at it.
Is that in the scope of the project as defined currently?
Yes. We want to demonstrate if it is cost effective or not.
We're coming up with an implementation plan now to see how actually we can get the idea more recognized and implemented in other projects, local agencies to start using it. More commonly doing FW testing, I guess, structural condition assessments. That's the direction.
Good.
All right. Thanks a lot.